Picture it. The universe had just been born, but instead of a glorious display of light and color, it was a vast, empty darkness stretching in all directions. Space wasn't filled with stars, planets, or glowing nebulae. It was filled with nothing interesting. No cosmic fireworks, no galactic clusters, just a quiet, invisible expanse of hydrogen and helium atoms slowly drifting apart. It was like the ultimate minimalist art installation, except no one was around to appreciate it. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. You could say this was the universe's version of a loading screen. The Big Bang had pressed the start button, but the main game hadn't begun yet. All the exciting stuff, stars, galaxies, black holes, and cosmic drama, was still buffering. The background music, just the faint hum of the cosmic microwave background, too quiet for anyone or anything to hear. If you could somehow stand in the middle of that early universe, you'd see, well, nothing. Literally. It wouldn't even be dark in the way we experience darkness, because there was no light for your eyes to register. There were no eyes either, of course, but hypothetically speaking, if you were there, you'd be staring into a perfectly uniform blackness that went on forever. It's the kind of scene that would make even a philosopher say, okay, this is a bit too much emptiness for me. And yet, hidden in that emptiness was everything. The seeds of galaxies were already there, written in the faintest ripples of density spread throughout space. Gravity, that invisible sculptor of structure, was biding its time. It's almost poetic. Before the universe could shine, it first had to be still. Before there could be creation, there had to be silence. The cosmos was gathering its breath before its first line. The first few 100 million years after the Big Bang were kind of like a cosmic intermission. The universe had expanded and cooled enough to settle into a calm, stable state. The wild chaos of its explosive birth was over, and now it was drifting, quietly, aimlessly, like a teenager unsure of what to do after high school. All that existed was potential energy, hydrogen atoms, helium atoms, and a vast amount of empty space between them. It's strange to think that something so uneventful was actually crucial. Without this long, silent stretch of nothingness, the universe wouldn't have had the time or conditions it needed for structure to form later on. If the cosmos had rushed into making stars too soon, gravity wouldn't have had enough time to gather the scattered material together. The darkness, as dull as it seems, was absolutely necessary. It was the calm before every storm that would ever follow. We often think of darkness as the absence of something. But in this case, darkness was full of possibility. It wasn't the end of something, it was the beginning, an invisible stage being built for the greatest light show in existence. The universe was in no hurry. It had time. And it needed time. If you could somehow look back at this era, you might find it eerie. There were no points of reference, no constellations, no swirling galaxies. Just a cold, thin fog of gas stretching endlessly. Every atom of hydrogen floating in that black sea had no idea it was destined to one day become part of a star, a planet, maybe even a brain thinking about the universe itself. Every atom was waiting for gravity's gentle pull to begin its cosmic career. In that sense, this early, starless universe wasn't empty. It was pregnant with potential. It's like staring at a blank page before a masterpiece is written, or hearing the faint static before a symphony begins. The silence wasn't meaningless. It was the foundation of everything that would come after. The first galaxies, the first stars, the birth of light, all of it depended on this period of quiet stillness. But from a storytelling point of view, this was the ultimate cliffhanger. The Big Bang had set up the plot, introduced the main characters, space, time, matter, but then left everyone hanging. Coming soon, the cosmos seemed to whisper, the light. For hundreds of millions of years, nothing much happened, and yet everything was building toward that moment. The great cosmic cliffhanger is a reminder that even the universe needed time to figure itself out. That sometimes the most important parts of a story happen off-screen, in silence, when nothing seems to be happening at all. It's the waiting that makes the first light so meaningful. So before there were galaxies swirling in brilliant spirals, before there were planets orbiting suns, before even a single star dared to shine, the universe existed in a quiet, invisible suspension. No noise, no light. Just endless, patient dark. It was the greatest pause in history, and it was about to set the stage for everything we now know as the cosmos. Let's rewind the cosmic clock to the very first few seconds after the Big Bang, when everything you know, everything you see, everything you are, was squeezed into a volume smaller than a pea. The moment space and time burst into existence, the universe didn't politely stretch its legs and say, "Ah, good morning." It screamed into being with temperatures so high that matter itself couldn't exist in any recognizable form. The entire cosmos was a furious inferno of energy, radiation, and chaos. This was not a place where atoms strolled around peacefully. In those first fractions of a second, the universe was a thick, glowing fog of fundamental particles, quarks, electrons, neutrinos, all zipping around at nearly the speed of light. They smashed into each other with energy so extreme that trying to describe it in ordinary human terms is like comparing a candle flame to the surface of the sun. The laws of physics themselves were still cooling off from their cosmic hangover. During this time, forces were separating like co-workers awkwardly dividing tasks on a group project. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, began to take on their own identities. In the very first moments, these forces might have been united in a single, elegant superforce. But as the universe expanded and cooled, symmetry broke. Gravity peeled off first, taking charge of shaping space itself, while the strong nuclear force got busy gluing quarks together into protons and neutrons. The weak force started handling radioactive decay, and electromagnetism became the universe's electrician, wiring up charged particles. After about 1/1,000,000th of a second, the first protons and neutrons appeared, tiny building blocks that would one day form the cores of atoms. It was the beginning of matter as we know it, But if you were somehow there, ignoring the fact that you'd be instantly vaporized, you wouldn't see any familiar shapes or colors. You'd just witness a blinding storm of subatomic chaos, a place where the distinction between energy and matter was practically meaningless. Over the next 3 minutes, yes, minutes, the universe performed its first great act of chemistry. In an event known as Big Bang nucleosynthesis, those newly formed protons and neutrons started fusing together under intense heat and pressure. It was like a cosmic kitchen where the only recipe was mix hydrogen and helium, serve hot. Within those first few minutes, about 75% of the universe's mass became hydrogen nuclei, and about 25% became helium nuclei. A sprinkle of lithium and beryllium showed up too, but that was about it. The periodic table, for now, was embarrassingly short. But even though the universe now had atomic nuclei, it still wasn't ready to make actual atoms. The temperatures were still absurdly high, millions of degrees. Any time an electron tried to join a nucleus to form an atom, some high-energy photon would come along and blast it apart again. It was like trying to hold a snowball together in a volcano. So, for hundreds of thousands of years, the universe remained a plasma, an opaque fog of charged particles and radiation bouncing endlessly off each other. Light couldn't travel far. It was constantly being scattered. The universe, ironically, was glowing everywhere but completely invisible from the inside. During this plasma era, space was expanding rapidly, dragging the particles and radiation with it. Expansion worked like the universe's built-in air conditioner. It stretched the wavelengths of light, cooling everything down. Gradually, the temperature dropped from billions of degrees to mere thousands. Compared to before, that was downright chilly. But it was only when the universe reached about 3,000 degrees that things started to get interesting. At that point, around 380,000 years after the Big Bang, the electrons finally slowed down enough for protons to capture them and form neutral hydrogen atoms. It was the cosmic equivalent of everyone finally calming down after a wild party. The universe transitioned from an opaque plasma to a transparent gas. For the first time, light could travel freely through space without constantly bumping into particles. This event, called recombination, released the oldest light we can still detect today, the cosmic microwave background. But at the moment it happened, no one was there to see it. There were no eyes, no observers, no galaxies yet to catch the glow. The light simply stretched outward with space itself, cooling over billions of years into the faint microwave radiation that now softly fills the cosmos. It's like the universe's baby picture. Grainy, faded, but still visible if you know how to look. The aftermath of the Big Bang was less like an explosion in space and more like an explosion of space. Every cubic centimeter of the cosmos was expanding, carrying matter and energy outward in all directions. It wasn't that things were moving through space. It was that space itself was growing, like dough rising with raisins scattered through it. From our perspective today, that expansion never stopped. It just slowed down enough for structures to start forming much, much later. If the Big Bang was the spark that lit the fire, then the aftermath was the long, glowing ember stage, the universe catching its breath after its own birth. It was messy, loud, and absurdly hot, but it was also astonishingly organized. In those early moments, the seeds of everything, stars, planets, life, were planted in the simplest of ways, through physics doing what physics does best. So, while the early universe may have looked like chaos, it was a very productive chaos. It set the rules, made the first matter, and left behind a cosmic fingerprint we can still read today. And once the heat faded and the light broke free, the stage was finally set for the universe's next act, the long, quiet darkness before the first stars dared to shine. When the universe finally cooled enough for atoms to form, it was like a cosmic curtain being lifted. For the first time, light could travel without getting immediately smacked in the face by a stray electron. Space went from being a blinding, foggy plasma to something clear and open. You might think this would be the moment the cosmos finally lit up, like someone flipped on the lights after the Big Bang's fiery chaos. But no, what actually happened was the opposite. The universe became transparent, yes, but also profoundly dark. Imagine a room full of smoke suddenly clearing, but the light bulbs all go out at the same time. That's what the cosmos experienced. The light that filled the early universe, those photons released when atoms finally formed, wasn't visible light anymore. As space expanded, those photons stretched, their wavelengths growing longer and redder until they slipped into the microwave part of the spectrum. The glow of creation dimmed into an invisible hum. This marks the beginning of what scientists poetically call the cosmic dark ages, a time when the universe existed, but nothing shone. There were no stars, no galaxies, and no bright sources of light anywhere. The universe was a vast, silent expanse of neutral hydrogen gas, cold and ghostly, floating in a sea of darkness. Every particle of matter was just minding its own business, scattered thinly across billions of light years. It's hard to imagine just how empty this was. Space wasn't filled with dramatic nebulae or clusters of galaxies. Those would come much later. If you could somehow stand there, assuming you could survive the vacuum, you'd see no stars, no planets, no glow, just the faintest whisper of the leftover radiation from the Big Bang, stretched thin and cool. Even time itself seemed to move differently then. There were no days or nights because there were no suns to rise or set, just eternal, unbroken night. But while the cosmos looked static, it wasn't idle. Gravity was quietly at work behind the scenes, nudging the gas ever so slightly toward clumping. The universe was like a calm sea that occasionally rippled from unseen tides. Those ripples, tiny differences in density left over from earlier quantum fluctuations, were the faint fingerprints of what would one day become galaxies. But in this chapter of the universe's story, nothing had yet collapsed into stars. The lights were out, and the stage was still empty. It's strange to think of darkness not as an absence, but as a phase of creation. The cosmic dark ages were, in many ways, the universe's incubation period. Everything was cooling, settling, and waiting for gravity to do its slow, deliberate work. The hydrogen atoms drifting through the blackness weren't useless. They were the raw ingredients of future suns. Each atom a seed with a destiny, unaware that in a few 100 million years it would be part of something that glowed bright enough to be seen across the universe. If we could somehow record this time period, it would sound eerily quiet. There were no crackles of radiation from exploding stars, no hum from galaxies colliding, just the faint, ever-cooling background radiation, an ancient echo of the Big Bang's heat, fading further into the cold. Even the temperature of the universe was dropping steadily, falling from thousands of degrees to just a few dozen over millions of years. If the early universe had been a raging bonfire, it was now little more than glowing embers, dimming into invisible heat. What makes this era fascinating is that, for all its emptiness, it set the stage for everything that came next. The cosmic dark ages were a test of patience. Hundreds of millions of years where the universe simply waited. No one was there to watch it happen, of course, but if there had been, it would have been a view so profoundly still it might have driven any observer mad. There was no up, no down, no sense of direction, because there was nothing to orient yourself against. You'd just float in an endless, silent ocean of hydrogen. And yet, beneath that stillness, the first cosmic structures were beginning to whisper into existence. Those small density ripples, the places where matter was just slightly thicker than average, began to attract more matter. Slowly, imperceptibly, clouds of gas started to gather. These were the first faint hints of cosmic geography forming. But for now, there was no light to mark their presence. Only physics could tell the story, not photons. Ironically, it's the very absence of light that allows modern astronomers to study this period. When telescopes peer into the deep universe, they're looking back in time. The farther they look, the younger the universe appears. But there's a limit, a wall of darkness where the first light hasn't yet switched on. That's the cosmic dark ages, the last truly unlit page in the universe's visible history. The light from that time is too faint, too stretched, too hidden for even our most powerful instruments to see clearly. If the Big Bang was the universe's birth cry, then the Dark Ages were its first breath, a long, silent inhale before the exhale of starlight. This wasn't the end of activity, but a deep pause, a cosmic meditation before the first stars ignited. It's humbling to think that every bright galaxy, every glowing star we see today was once part of that same cold, invisible gas. Darkness wasn't the enemy of light, it was its cradle. So, when we look up at the night sky now, scattered with stars, we are really seeing the after-party. The lights that came on after billions of years of waiting. But long before all that, there was a time when the universe was an endless, soundless void, humming softly with leftover radiation, and holding its breath for the first time something would shine. The birth of darkness wasn't a failure of the universe to glow. It was the universe preparing the canvas. The light would come later, brilliant and transformative. But first, there had to be stillness. First, there had to be the dark. After the universe cooled and the first atoms formed, what followed was an age of astonishing simplicity. The chaos of the Big Bang was over, the fog had cleared, and now the cosmos found itself in a kind of minimalist phase. Hydrogen and helium, those two humble gases, were the only ingredients on the menu. If the early universe were a kitchen, it would have been one of those pretentious restaurants that serves air foam as a main course. 92% hydrogen, 8% helium, and a microscopic sprinkling of lithium. That was it. The universe was breathtakingly vast, but chemically speaking, it was about as interesting as a bowl of lukewarm water. This era, let's call it the reign of hydrogen, was when the cosmos entered its quiet middle age. The drama of expansion had slowed, and the wild fusion party of the Big Bang's aftermath was long over. The universe was no longer a furnace. It was cool, stable, and astonishingly uniform. Everywhere you looked, if you could have looked, you would see the same endless expanse of nearly identical gas. No stars burning, no galaxies spinning, no explosions, just hydrogen and helium drifting apart, like shy dance partners waiting for someone to make the first move. Hydrogen, the simplest and most abundant element in the universe, was the clear ruler of this age. Each atom, a single proton with one electron, was a masterpiece of simplicity. And yet, that simplicity was deceptive. Hydrogen wasn't just filling space, it was storing potential. Hidden within those lonely atoms was the fuel that would one day ignite the first stars, forge the first heavy elements, and make the universe sparkle. But for now, hydrogen was content to float in near-perfect uniformity, spreading thin across billions of light years. If you could somehow fly through this era, you'd be passing through a place both empty and full. On average, there was less than 1 atom per cubic meter, so empty you could travel for years without bumping into a single particle. But stretch that across the incomprehensible scale of the cosmos, and the total amount of hydrogen was staggering. It filled every corner of existence. Space was both a vacuum and an ocean, depending on how you looked at it. Helium, hydrogen's quieter companion, made up the rest. It didn't react much with anything. Helium's the cosmic introvert of the periodic table. Together, these two gases drifted silently, forming vast, invisible clouds. Occasionally, random chance or the tiniest fluctuations in density caused some areas to be just slightly denser than others. These were the first hints of cosmic structure, the faintest gravitational whispers. But the universe didn't yet have the patience, or rather the time, to turn those whispers into something tangible. Everything was still settling, smoothing out after its fiery beginning. You might imagine the hydrogen era as an age of cosmic peace, but peace can also be boring. There were no colors, no light, no sound. The only thing happening was the slow dance of atoms under gravity's faint influence. Every now and then, gravity would start to tug at a patch of hydrogen just a little harder. Those patches began to attract more gas, and slowly, imperceptibly, small clumps started to form. These clumps were the universe's first attempts at organization, its first drafts of galaxies and stars. But make no mistake, this process took time. Cosmic time. Millions upon millions of years passed without anything you could call interesting happening. The hydrogen era was a marathon, not a sprint. The universe expanded, cooled, and spread its gas thinner and thinner. The temperature of space dropped to just a few dozen degrees at above absolute zero. If the Big Bang had been a roaring fire, this was the ash settling afterward. Cold, quiet, but full of potential energy waiting to be rekindled. Hydrogen itself, despite being so simple, has a kind of quiet genius. It's the ultimate building block, small, abundant, and ready to bond under the right conditions. But in this early age, there were no conditions to make it bond into anything interesting. The temperatures were too low for fusion, and the density too sparse for chemical reactions. It was like owning all the ingredients for a meal but having no stove to cook it. Everything was raw, inert, and patient. Yet even in this stillness, physics was laying the groundwork for creation. Gravity continued to play the long game, pulling gently at those hydrogen clouds. Over time, those tiny differences in density became amplified. Dense regions grew denser, while thin regions thinned out even more. The seeds of structure were germinating. If you could fast forward through time, you'd see faint ripples turning into sprawling filaments, forming the cosmic web that still defines the shape of the universe today. But in the moment, it was all invisible, all silent. This era is sometimes overlooked because on the surface, it's not dramatic, but it was essential. It was the calm between storms, the quiet moment that allowed gravity to sculpt the universe's grand design. Without this long hydrogen-dominated interlude, the cosmos would never have formed stars, planets, or life. The hydrogen era was like the mixing phase before baking a cake. Everything getting distributed, blended, and prepared for the heat to come. It's also oddly poetic that the simplest element became the foundation for all future complexity. Every molecule of water, every breath of oxygen, every carbon atom in your body owes its existence to hydrogen's willingness to fuse later in stars. In this early age, hydrogen didn't look like much, but it was the universe's hidden masterpiece. So, during the hydrogen era, space wasn't a void of nothingness. It was a vast waiting room filled with the quiet hum of potential. The stage was set. The actors, hydrogen and helium, were in place, and gravity was about to cue the next act. The lights were still off, but behind the scenes, the universe was rehearsing for its most spectacular performance, the birth of the very first stars. In the quiet aftermath of the hydrogen era, when the universe was a dark, endless ocean of gas, one invisible force began to stir things up. Gravity, subtle, patient, and utterly relentless, was about to take charge. If the cosmos were a blank canvas, gravity was the hand that would start sketching. And it didn't rush. It worked with the patience of a sculptor carving from fog. You might think of gravity as a kind of cosmic artist with a taste for drama. Its tools? Nothing more than mass and time. Wherever there was just a little more matter than average, a slightly denser patch of hydrogen or helium gas, it began to tug ever so gently on its surroundings. These were not big clumps at first, just tiny fluctuations, the faint ripples left over from the earliest quantum jitters in the Big Bang. But in a universe governed by gravity, small differences have big consequences. To understand how gravity worked its magic, imagine tossing a handful of sand onto a trampoline. Each grain makes a tiny dip in the surface, bending it ever so slightly. If you add more grains, the dip deepens and other grains start rolling toward it. That's what gravity does to space itself. It bends it around matter, causing more matter to fall in. The more that gathers, the stronger the pull becomes, and the faster the process accelerates. It's a cosmic feedback loop, quietly sculpting structure from chaos. But this process didn't happen overnight. The universe was expanding, and expansion worked against gravity's ambitions. Every time gravity tried to pull matter together, cosmic expansion tried to stretch it apart again. The two forces were locked in an ancient tug of war, one pulling inward, the other pushing outward. For millions of years, this tension shaped the fate of everything. In the darkest corners of space, where hydrogen gas was ever so slightly thicker, gravity began winning. Those regions started to attract more gas, slowly forming what astronomers call dark matter halos. Now, dark matter, mysterious stuff we still don't fully understand, doesn't emit or absorb light, but it has mass and therefore gravity. It acted as scaffolding for the visible universe, creating invisible wells that ordinary matter began to fall into. Think of dark matter as the cosmic skeleton, an unseen frame holding everything in place while visible matter draped over it like skin. As hydrogen and helium clouds drifted into these gravitational wells, they began to swirl. The denser the cloud became, the stronger its gravity pulled, and the faster it spun. Picture massive whirlpools forming in an ocean of gas, silent, cold, and impossibly vast. These whirling clouds would eventually become the cradles of the first stars, but at this stage they were just gathering mass, thickening under their own weight. If we could watch this process unfold in time-lapse, it would look like a slow, grand ballet. Regions of slightly higher density began to glow, figuratively speaking, since there was no light yet, with potential. Tiny clumps merged into bigger clumps, filaments stretched between them, and a cosmic web began to take shape. What had once been a smooth, uniform universe was now becoming textured, structured, alive with gravitational intent. But gravity isn't gentle. The same force that holds your feet to the floor also crushes entire clouds of gas under unimaginable pressure. As these clouds grew denser, the atoms inside began colliding more frequently, generating heat. The centers of these collapsing regions grew hot enough that eventually something extraordinary would happen: nuclear fusion, the birth of stars. But that moment still lay far ahead. For now, gravity's only masterpiece was structure itself. During this time, gravity didn't just shape matter, it shaped time. In denser regions, time actually ticked slightly slower due to the way gravity bends space-time. It's a strange thought. The first pockets of future galaxies were not only forming matter, but distorting the flow of time itself. The deeper the gravitational well, the slower the clock ran. Even then, the universe was playing with the concept of relativity, long before Einstein gave it a name. Of course, not every region of space was destined for greatness. Many of the smaller clumps failed to grow, their gas dissipated by cosmic expansion before gravity could fully take hold. Others merged with larger structures, losing their individuality in the process. But even these failures were part of the pattern, feeding the larger formations that would one day become galaxies. It was a cosmic version of natural selection. Only the densest, most gravitationally ambitious clouds survived. What's remarkable about this era is how quiet it was. No explosions, no flashes, no visible drama. Just the slow choreography of atoms responding to an invisible hand. And yet, this was one of the most crucial acts in cosmic history. Without gravity's steady persistence, the universe would have remained a formless sea of hydrogen forever. No stars, no planets, no us. Everything that followed, the birth of light, the chemistry of life, owed its existence to gravity's patient insistence that space could be more than emptiness. It's easy to overlook gravity because it feels ordinary. We experience it every day. But on the cosmic scale, it's anything but ordinary. It's the one force that doesn't let go. It binds galaxies, bends light, and dictates the architecture of the entire universe. During this ancient era, gravity was composing the first great symphony of structure, a melody too slow for human ears, but destined to echo through billions of years. So, as hydrogen clouds gathered and filaments formed across the vast black canvas, gravity continued its quiet work, oblivious to time. It didn't need to hurry. The universe was its playground, and patience its greatest power. Those first faint clumps of matter were the universe's way of whispering its next act into existence, a promise that from darkness would come form, and from emptiness, creation. When we picture the early universe, it's tempting to imagine a perfectly even ocean of gas, smooth, flawless, and serene. But that would be the wrong image. The early cosmos was not a uniform void. It was full of tiny imperfections, microscopic differences in density scattered throughout space. These irregularities, though small, were the most important blemishes in the history of everything. Without them, the universe would have stayed a dull, featureless fog forever. These ripples were the aftershocks of quantum fluctuations, minute wobbles in energy that occurred during the universe's infancy when it was still smaller than an atom. In the strange world of quantum mechanics, nothing is ever truly still. Even empty space trembles with uncertainty, with particles flickering in and out of existence faster than a hummingbird's heartbeat. When the universe expanded explosively during inflation, a hyperfast ballooning that happened in a fraction of a second, those tiny quantum jitters were stretched to cosmic scales. What began as subatomic noise became vast ripples in space-time itself. Imagine inflating a balloon with tiny specks of dust on its surface. As the balloon grows, those specks spread out, but their relative positions remain. The early universe worked in much the same way. Inflation took the quantum wrinkles in the fabric of space and blew them up to sizes billions of light-years across. Those wrinkles became regions that were ever so slightly denser or emptier than average. We're talking differences as small as 1 part in 100,000. But those differences would decide everything. After inflation ended, these ripples in density became the seeds of structure. Where there was slightly more matter, gravity had a head start. Those spots would grow denser over time, pulling in more gas and dark matter. Where there was slightly less matter, gravity had less to work with, and those regions would become cosmic voids, vast stretches of near-empty space separating the galaxies we see today. The entire cosmic web, the intricate, interconnected network of galaxies spanning the universe, was written in these tiny variations. In many ways, the universe's imperfections were its greatest strength. Perfect symmetry might sound elegant, but in cosmology, perfection means nothing ever happens. A perfectly uniform universe would have been gravitationally static. No pull, no collapse, no stars. Everything would have expanded evenly forever. A bland soup of hydrogen drifting through eternal night. It's those little ripples, those tiny mistakes in cosmic symmetry, that made existence interesting. You, me, and every galaxy owe our existence to a fraction of a percent's worth of unevenness. The evidence for these primordial ripples is still visible today, frozen in the light of the cosmic microwave background, the faint afterglow of the Big Bang. When scientists mapped this ancient radiation with satellites like COBO, WMAP, and Planck, they discovered faint blotches and patterns in temperature and density. Those blotches are the fingerprints of the first fluctuations, preserved across billions of years. They show where matter was slightly denser or thinner, the places where galaxies would one day cluster or where great cosmic voids would stretch. To the untrained eye, that map looks like a random patchwork of red and blue spots, but hidden in that chaos is the entire blueprint of the universe. The size and spacing of those ripples reveal how fast the universe expanded, how much dark matter it contains, and even how geometry itself behaves on the largest scales. In other words, those tiny ancient wrinkles still whisper secrets about the birth and fate of everything. It's fascinating to think that randomness, something we often associate with chaos or disorder, was the architect of structure. The fluctuations were random in origin, but not meaningless. They followed the laws of quantum physics, amplified by inflation, sculpted by gravity. Out of randomness came order. Out of noise came pattern. It's as if the universe composed its own symphony by letting the instruments tune themselves. The most poetic part of this story is that the cosmic ripples were utterly silent. No waves of sound echoed through the vacuum. These were ripples in density, not air pressure. Yet they behaved almost like a cosmic symphony in slow motion, regions of higher and lower density oscillating over millions of years. If you could somehow hear it, the sound would be a deep, resonant hum spanning across time itself. The universe didn't just expand, it sang. But during this early period, these ripples were incredibly faint. The universe was still dark, and no light illuminated these structures yet. Everything happened quietly, invisibly in the background. The ripples were the storyboards of galaxies yet to form. Gravity would later come in to amplify them, turning slight differences into grand cosmic architecture. But the script had already been written in the subatomic vibrations of the newborn universe. If you could zoom in on one of these ripples during the Dark Ages, you wouldn't see much. A slightly denser patch of hydrogen gas surrounded by emptier regions. Yet over millions of years, that patch would begin to pull in more matter, and then more still, until eventually it became a glowing ball of fusion. The first star. Every beam of light you see in the night sky began as one of these ancient ripples, amplified by gravity and ignited by physics. So the next time you gaze up at the stars, remember that their positions are not random. The galaxies, the clusters, even the vast voids between them, all trace back to those first quantum tremors. The universe's very structure, from the Milky Way's swirling arms to the empty expanses beyond, is a magnified echo of the smallest vibrations possible. In the end, those ripples in the darkness were the universe's earliest creative act. A whisper of imperfection that became everything. The cosmos didn't need perfection. It needed a few wrinkles. And from those wrinkles the universe unfolded, messy, beautiful, and full of light waiting to be born. By this point in the story, the universe had been dark for hundreds of millions of years, quiet, vast, and full of gas. Gravity had started its patient work, pulling scattered hydrogen and helium together into gentle clumps, the faint beginnings of structure. But these gas clouds faced a problem. They were too warm to collapse. Every time gravity tried to compress them, the gas inside pushed back, like a cosmic balloon refusing to pop. For stars to form, the universe needed to invent a way to cool down. Cooling might sound simple. Just lose some heat, right? But in the early universe, nothing about cooling was easy. You couldn't just radiate energy into the air because, well, there was no air. The only available ingredients were hydrogen, helium, and a smattering of lithium, none of the complex molecules we have today that make cooling efficient. The universe had to work with what it had, and that meant finding clever ways to shed energy using just those primitive elements. At first, the expansion of space itself did much of the cooling. As the universe stretched, the wavelengths of light stretched too, and energy spread thinner. Imagine blowing up a balloon painted with bright colors. The colors fade as the surface expands. That's what happened to radiation in space. It lost energy, lowering the overall temperature of the cosmos. But for individual gas clouds, this wasn't enough. If gravity wanted to pull hydrogen atoms close enough to ignite a star, it needed the gas to get dramatically colder, cold enough that atoms would huddle together instead of bouncing apart. Enter molecular hydrogen, the universe's first molecular miracle. Under the right conditions, two hydrogen atoms could link up, forming the simplest molecule possible, H2. This tiny pairing was no small thing. Unlike single hydrogen atoms, which are terrible at losing heat, molecular hydrogen could vibrate and rotate, giving it a way to release energy as faint infrared radiation. Every time a hydrogen molecule wiggled, it radiated away a bit of warmth. Slowly, patiently, entire clouds began to cool. It's funny to think of molecular hydrogen as the cosmos's first air conditioner, but that's exactly what it was. These molecules allowed the gas to drop from thousands of degrees down to just a few hundred, a crucial difference. Once cool enough, the internal pressure weakened, and gravity could finally take charge, drawing matter inward toward denser centers. Without this molecular cooling, the first stars would never have been born. The entire universe would have remained a lukewarm, featureless expanse, forever stuck in its awkward, gassy adolescence. But the process wasn't smooth or uniform. Some regions cooled faster than others, depending on how dense the gas was and how efficiently molecular hydrogen formed. In the densest regions, cooling cascaded. Cold gas drew in more gas, which cooled even further, creating runaway pockets of collapse. In the emptier regions, however, the gas remained stubbornly warm and diffuse. This uneven cooling created contrast, the beginnings of cosmic geography. These cooling clouds grew denser at their cores, forming what astronomers later called protostellar halos. Each halo was a cosmic embryo, vast clouds of gas and dark matter, hundreds of light years wide, where temperatures began to plummet. Inside these halos, gravity worked overtime, compressing the gas until it glowed faintly from frictional heat. Yet even as it heated locally, the molecular hydrogen kept bleeding energy away, allowing the overall structure to tighten. The tug-of-war between compression and cooling was delicate, but it was exactly what the universe needed. The cooling process also set the stage for chemistry's first baby steps. When gas cooled, atoms moved slower, which increased their chances of sticking together during collisions. This led to the first formation of simple molecules. Hydrogen molecules, a trace of helium hydride, and even a whisper of lithium hydride. These were the universe's very first chemical compounds. Tiny sparks of molecular creativity in a cosmos otherwise dominated by simplicity. As temperatures dropped, so did the pace of motion. The universe was still expanding, but within those growing protostellar regions, the gas was beginning to behave differently. Instead of freely drifting, it was gathering into dense filaments, twisting and spiraling inward like slow cosmic whirlpools. Each filament was a future nursery for stars, but for now, they were just cold, dark rivers of hydrogen weaving through the blackness. If we could have watched this era unfold, we wouldn't have seen light, we'd have seen movement. Cold gas drifting, clumping, merging in silence. No glow, no explosions, no color. Yet beneath that stillness, potential energy was building. Cooling didn't just allow collapse, it demanded it. Once gas got cold enough, gravity took over completely, squeezing the densest regions into tighter and tighter knots. Cooling also determined the size and shape of the first stars to come. In places where molecular hydrogen cooled gas efficiently, smaller, denser fragments formed. Where cooling was less effective, clouds stayed massive, leading to the creation of enormous stars. Giants hundreds of times the mass of our Sun. These early stars would later burn hot and fast, flooding space with radiation and rewriting the chemistry of everything. But that was still far in the future. For now, the universe was mastering the art of transformation through patience. The cosmic soup that had once been uniform and hot was learning how to settle, to calm, to breathe. Each molecule of hydrogen was part of a vast, slow choreography, losing just enough energy for gravity to shape it into something new. Cooling was the first step toward complexity, the quiet foundation beneath every galaxy and star that would ever exist. In the grand symphony of cosmic creation, cooling played the softest notes, but without them, the melody could never begin. The universe was learning restraint. Before it could blaze with light, it had to learn to chill. And as it cooled, the first pockets of structure began to whisper with possibility. The gas clouds that had once drifted aimlessly were now dense and cold, primed for ignition. The universe, for the first time, was truly ready for stars. After all the cooling, condensing, and quiet sculpting, the universe found itself in a strange kind of limbo. Everything was ready for something to happen, but nothing had happened yet. Hydrogen and helium clouds drifted through the darkness. Gravity continued its patient work, and molecular hydrogen quietly leaked away warmth like a cosmic air conditioner on its lowest setting. The conditions were perfect for creation, but the spark had not yet struck. The universe was, quite literally, killing time. If the earlier epochs were filled with transformation, the Big Bang, the cooling plasma, the birth of atoms, this was the age of anticipation. The cosmos was now hundreds of millions of years old, which sounds like an eternity to us, but, in universal terms, it was still early morning. Everything was in slow motion. The first star hadn't yet been born, and so the universe was dark in the truest sense. No light, no glimmer, not even a distant reflection. Just the faint glow of the cosmic microwave background, an ancient whisper from a much hotter past, spreading thinner with each passing eon. In this age of cosmic patience, silence ruled. There was movement, of course, hydrogen and helium swirling, gravity pulling, but it was almost imperceptible. If you could fast forward through this time in a cosmic time-lapse, you'd see faint threads of gas stretching, twisting, and merging into denser regions. But in real time, it was a crawl. Nothing exploded. Nothing ignited. It was the universe's version of a long, silent inhale before the exhale of starlight. The density variations, those faint imprints left by quantum ripples, were slowly amplifying. In denser patches, gravity was gently winning the tug-of-war against cosmic expansion. Hydrogen gas trickled inward, forming the faintest outlines of what would later become galaxies. These were embryonic structures, clumps and filaments so diffuse that you could travel through them for light years without hitting a single atom. Yet even in their near emptiness, they were history's first architectural sketches. Every so often, gas clouds would begin to compress under their own weight, only to stall again. Cooling helped, but not quite enough. The process was excruciatingly delicate. Too hot, and the gas would expand back out. Too cold, and gravity's grip would loosen. The universe didn't yet have metals or dust, the efficient coolants that later generations of stars would rely on. It was like trying to light a campfire with wet wood and no kindling. Everything was set up for combustion, but the first spark was maddeningly hard to catch. Meanwhile, dark matter continued to do its silent, invisible work. Though it couldn't cool or collapse like gas, it provided the gravitational scaffolding, the unseen framework where ordinary matter could gather. These halos of dark matter were slowly deepening their wells, making it easier for hydrogen clouds to settle within them. Without dark matter's gravitational stage, the show might never have started at all. But even with that invisible help, time dragged on. It's humbling to think how long the cosmos lingered in darkness, how patient it was before bursting into light. For hundreds of millions of years, the only thing happening was waiting. But that waiting wasn't wasted. It was essential. The gas clouds needed time to grow massive enough for gravity to truly take over. Every slight increase in density mattered. Every whisper of compression brought the universe closer to ignition. You might say this was cosmic fermentation, everything blending and maturing until the ingredients were just right. If an observer could somehow exist during this age, floating in the abyss, they would see a sky utterly devoid of features. No stars, no planets, not even faint glows, just darkness stretching forever. And yet, behind that darkness, invisible forces were choreographing a masterpiece. Every molecule of hydrogen drifting through that black void was on a slow path toward destiny, some destined to fuse into light, others to become planets, oceans, or lungs. But for now, everything waited. This waiting period also set the rhythm of the universe's future. It established the pacing of cosmic evolution, the balance between explosive creation and long, quiet interludes. The universe doesn't rush. It unfolds in its own time, and this era was proof of that. It's as though creation itself paused, gathering momentum for the first great leap forward. The silence wasn't emptiness, it was potential energy, coiled like a spring. The long wait also tested the universe's endurance. The expansion of space continued relentlessly, stretching matter farther apart, making gravity's job harder. Many regions that began to collapse simply couldn't hold together. They dispersed back into the dark. Others clung on, barely resisting the pull of expansion, slowly thickening until their cores grew dense enough to heat again. These would become the first protostars, but at this point they were still invisible, embryos forming in a womb of hydrogen. This era also carried an emotional irony. The universe had everything it needed for light, but couldn't yet make any. All the ingredients were in the bowl, but the recipe hadn't reached the oven. You could say the cosmos was like a matchbox full of potential, waiting for friction. When gravity finally concentrated enough matter in one place, temperatures would soar to millions of degrees, and hydrogen atoms would begin fusing into helium, releasing light for the first time. But until that moment, the darkness held absolute dominion. It's difficult for us to grasp the scale of this waiting game. Hundreds of millions of years passed in quiet preparation. From our perspective, it feels eternal, but to the universe, it was merely a deep breath. This was the prelude, the setup, the long-held silence before the orchestra of stars began to play. And when the first light finally pierced the void, when gravity's long work finally ignited hydrogen into fusion, it would be as if the universe opened its eyes for the very first time. But before that cosmic dawn, there was this, the long, quiet anticipation. The universe waiting for its own spark, holding its breath in the darkness, poised between nothing and everything. After hundreds of millions of years of silence, the universe finally broke its long, dark pause. In the deep void, hidden within vast clouds of hydrogen, the first true stars flickered into existence. It wasn't a gentle sunrise, it was a series of explosions of brilliance, brief and blazing. The universe, which had slumbered in near-perfect darkness since its birth, suddenly found itself pierced by light. It was the dawn of the first starlight, and with it, the universe was about to become a very different place. These first stars, known as Population 3 stars, were nothing like the ones we see in the sky today. They were enormous, primal beasts of fire. While our Sun is a relatively modest, long-lived star, these early titans were hundreds, even thousands of times more massive. The reason lay in their composition. Pure hydrogen and helium, untouched by heavier elements. Without metals or dust to help them cool, the first collapsing gas clouds formed massive cores before fusion could even begin. The result? Giants so hot and dense that when they finally ignited, they blazed with an intensity that outshone entire galaxies. Fusion began at the heart of these stellar giants when gravity's unrelenting pressure forced hydrogen atoms to smash together, creating helium and releasing a flood of energy. Each fusion reaction unleashed light and heat, and for the first time, the darkness was broken by starlight. The universe had its first lamps. It's almost poetic. Gravity, which had spent eons pulling the cosmos together in silence, finally created something capable of shining back against the void. When those first photons streamed into space, they illuminated a universe that had never known light before. Imagine that. For hundreds of millions of years there had been only darkness, and then, in an instant, brilliant, ultraviolet light spilled across space. It scattered through hydrogen clouds glinting off filaments of gas like faint cosmic fog. For the first time, shadows existed. The universe, which had been timeless and featureless, now had contrast. But these early stars were not gentle suns nurturing planets and life. They were monsters, furious, volatile, and unstable. Their lives were measured not in billions of years, like our suns, but in just a few million. They burned through their fuel with reckless abandon, their immense cores fusing hydrogen into helium, then helium into heavier elements, until they reached the limits of what fusion could sustain. When they died, they did not fade quietly. They detonated as supernovae, cataclysmic explosions that ripped themselves apart and hurled newly forged elements into the cosmos. Those explosions were as creative as they were destructive. In their violent deaths, the first stars scattered carbon, oxygen, silicon, and iron, the universe's first heavy elements, into the surrounding space. Before them, there had been nothing but hydrogen and helium. After them, there were the building blocks for planets, for oceans, for life. In other words, everything complex, every atom in your body heavier than helium, was born in the violent deaths of these first stars. We are, quite literally, the ashes of cosmic fire. And, though they were rare and brief, the light of these first stars began to transform the universe on a grand scale. Their intense ultraviolet radiation started to strip electrons from nearby hydrogen atoms, a process called ionization. For hundreds of millions of years, space had been filled with neutral hydrogen gas that absorbed light. Now, these stars began to burn it away, clearing the cosmic fog. Slowly but surely, the opaque universe became transparent once more, paving the way for the brilliant, structured cosmos we see today. If you could have stood in that young universe, though stood isn't quite the word, since there were no planets yet, you would have seen vast regions of darkness pierced by brilliant, isolated points of light. Each point was a titanic furnace, flooding its local bubble of space with radiation. Around them, ionized hydrogen formed glowing halos, expanding outward as the starlight carved cavities in the dark. It would have been the most dramatic light show imaginable, the first dawn written in fire. But while these stars illuminated the universe, they also sowed chaos. Their intense radiation heated nearby gas, preventing smaller clumps from collapsing and delaying the formation of future stars. Their supernovae blasted shock waves through space, stirring up clouds and triggering new collapses in some regions while dispersing others entirely. The universe was learning the rhythm of creation and destruction, a cosmic heartbeat that would continue for billions of years. It's humbling to think how short-lived these first stars were. They came and went long before the Milky Way existed, before any planet had formed, before even the concept of time as we know it had taken on meaning. Yet their brief lives set everything in motion. Their deaths seeded the cosmos with metals, enabling later generations of stars to form smaller, cooler, and more stable systems, the kind that could eventually host planets. These pioneers were never meant to last. Their purpose was to ignite the chain reaction that would lead to everything else. The birth of the first stars marked a turning point. The universe was no longer just expanding. It was evolving. Light had returned, chemistry had advanced, and structure was blooming across the cosmos. The black canvas that had persisted for so long was now dotted with luminous strokes, the first sketches of the galaxies to come. If the earlier epochs were the universe's prelude, then this was its opening act. The first flickers of light weren't just illumination, they were revelation. The cosmos had finally found its voice, and it spoke in the language of starlight. From here on, the universe would never again be truly dark. The fireworks of those first stars burned bright and brief, but their echoes endure. Every galaxy, every shining sun, every warm breath we take traces its lineage back to that first cosmic spark. The long night was over. The universe had awakened, and it began to glow. The universe's first stars didn't just shine. They cooked. Inside their scorching cores, atomic alchemy was underway. What began as simple hydrogen and helium was slowly forged into something entirely new. It was as if the cosmos had discovered chemistry for the first time, transforming the bland ingredients of creation into a dazzling buffet of elements. And when those colossal stars died, they didn't just vanish. They spilled their recipes across space, enriching the universe with the materials for everything that would ever exist. Up until this point, the universe had been breathtakingly simple. Hydrogen made up most of it. Helium filled in the gaps, and lithium barely registered as a rounding error. That was it. The cosmic pantry was practically empty. But when those first-generation stars, those gigantic, short-lived beacons, ignited, they began changing that forever. In their cores, unimaginable pressures squeezed atomic nuclei together, fusing them into heavier elements. Hydrogen became helium. Helium became carbon, oxygen, and nitrogen. And deeper still, iron was born in the hearts of the most massive stars. Fusion was the stars' secret art form, and like any artist, they paid a price for their work. As each new element formed, the balance inside the star shifted. Heavier elements built up in layers, like an onion of nuclear fire. Each layer burned at a higher temperature, and each step took the star closer to its own destruction. When it could no longer fuse elements to produce energy, the core collapsed under its own weight, and then everything exploded. A supernova is not just a violent death, it's a creative act. The collapse of the core sends a shock wave roaring outward, compressing and heating matter to such extreme conditions that even heavier elements like gold, silver, uranium, and platinum are forged in the chaos. In the blink of an eye, the dying star becomes the universe's first factory, spewing its newly minted treasures into the cosmos. Space, once filled with nothing but gas, now shimmered with dust, ash, and metal, the raw materials of planets and life. These explosions seeded the surrounding hydrogen clouds with new ingredients. Over time, as the next generation of stars formed, they incorporated these heavy elements into their cores and atmospheres. Each stellar generation added more complexity to the cosmic mix. What started as a universe with 3 elements slowly blossomed into one, with dozens, then hundreds. It was a chemical revolution on a universal scale, one that would lay the foundation for everything from the iron in your blood to the silicon in your phone. The distribution of these elements wasn't uniform. The first stars had exploded in random places, scattering their material unevenly. Some regions became rich in carbon and oxygen, while others accumulated heavier metals. This uneven distribution would later determine where planets could form, where atmospheres could emerge, and ultimately, where life could take hold. The chemistry of a region became its cosmic fingerprint, shaping its future evolution. The dust produced by these stellar deaths was especially important. Though it might sound unglamorous, dust is the universe's great builder. These tiny grains, made of carbon and silicates, provided surfaces where atoms could cling together, forming molecules. They cooled the gas, shielded it from radiation, and helped shape the clouds that would collapse into new stars. Dust turned the universe from a sterile expanse into a fertile environment, a cosmic garden where chemistry could bloom. As more supernovae erupted, the interstellar medium became a rich soup of elements. For the first time, the universe had the ingredients for water, organic molecules, and rocky worlds. Oxygen combined with hydrogen to form water vapor. Carbon bonded with hydrogen and nitrogen to form complex organic compounds. None of this existed before stars lived and died. The cosmos was learning to recycle, and with each generation of stars, it grew more intricate. This process of enrichment took time, millions upon millions of years. But with each new cycle, the universe's chemistry deepened. Second-generation stars, born from the ashes of their ancestors, burned more efficiently and lived longer. They, too, produced and spread elements, though in smaller, steadier quantities. Eventually, entire galaxies became alchemical engines, places where gas, dust, and radiation combined in endless creative loops. You could think of this era as the universe discovering color. Before the first stars, the cosmos was monochrome, dark hydrogen and helium gas, faintly illuminated by the dying glow of the Big Bang. Now, thanks to this chemical enrichment, the universe began to glow in new shades. Different elements absorbed and emitted light at unique wavelengths, creating a spectrum of hues across space. The cosmos, once uniform and gray, had become vibrant, textured, and alive with variation. And then, somewhere down the line, one of those later generations of stars would form a small, stable yellow sun. Around it, a disk of dust and gas rich in carbon, oxygen, silicon, and iron would swirl. From that material, planets would coalesce, and one of them would be just right, neither too hot nor too cold, for liquid water to exist. On that planet, those same elements forged in ancient stars would eventually assemble into something extraordinary. Life that could look up, see the stars, and wonder where it came from. The cosmic chemical revolution didn't just change the universe's composition, it changed its destiny. It turned physics into chemistry, and chemistry into biology. Every breath you take is a quiet echo of fusion reactions that happened billions of years ago. Every atom in your bones was once part of a star that exploded before the Earth even existed. So, when we talk about stardust, it's not a metaphor, it's a literal truth. The universe began as a simple recipe, but it was through fire, death, and rebirth that it found flavor. The first stars may have burned out long ago, but their legacy lingers in everything, from mountain stones to human thoughts. The cosmos didn't just make elements, it made possibilities. The periodic table is its love letter to creation, written in light, dust, and the ashes of stars. The first stars had arrived like sparks in the void, but their light was more than just illumination, it was transformative. Each new star became a beacon of fierce radiation, flooding the surrounding space with ultraviolet energy strong enough to change the very fabric of the universe. The cosmos, which had been shrouded in a fog of neutral hydrogen since the end of the Dark Ages, was about to undergo one of its greatest makeovers. This wasn't just the dawn of light, it was the dawn of clarity. To understand what happened, imagine the universe as a vast ocean of invisible mist. For hundreds of millions of years, this mist, made of neutral hydrogen atoms, had filled space, scattering and absorbing light. Even when the first stars began to shine, their glow could only reach so far before being swallowed by that thick hydrogen fog. The universe wasn't dark anymore, but it still wasn't clear. Light couldn't travel freely across cosmic distances. Then came reionization, the moment when that fog finally lifted. The ultraviolet light pouring out of young stars and galaxies carried enough energy to rip electrons away from hydrogen atoms. Each photon acted like a tiny cosmic chisel, breaking apart atoms and turning neutral hydrogen into a plasma of free protons and electrons once again. As these regions of ionized gas expanded and overlapped, they transformed the opaque universe into one that was transparent. It's a strange twist of fate. Billions of years earlier, when the universe first cooled and atoms formed, that event had made space transparent for the first time. Now, after the birth of the first stars, the opposite process, ripping those atoms apart again, made the universe transparent again. The difference this time was that it stayed that way. Once reionization finished, light could finally move freely across the cosmos, unimpeded by the fog of neutral gas. For the first time since the Big Bang, the universe became truly visible. This transformation didn't happen overnight. It unfolded gradually, over hundreds of millions of years, beginning roughly 400 million years after the Big Bang and finishing about 1 billion years later. Picture it like a cosmic sunrise. At first, just a few bright patches appeared in the darkness, the immediate surroundings of young stars and galaxies glowing as they ionized nearby hydrogen. Over time, these glowing bubbles expanded, spread, and merged until the entire universe was filled with light. But this was no peaceful dawn. Reionization was messy, energetic, and violent. The ultraviolet radiation from the first stars and galaxies blasted through their surroundings, heating and reshaping the intergalactic medium. The neutral hydrogen gas that had drifted quietly for eons was suddenly bombarded by photons energetic enough to strip away its electrons. In some regions, the radiation from clusters of early galaxies carved out vast cavities of ionized gas, while in others, denser hydrogen clouds stubbornly resisted, casting dark shadows across the cosmic landscape. And the first stars weren't alone in this work. As time went on, new actors joined the stage, the earliest black holes. Some of those massive first stars ended their lives not in fiery explosions, but in collapses so complete they left behind black holes dozens of times heavier than the Sun. These black holes began feeding on nearby gas, releasing enormous amounts of X-rays in the process. Unlike ultraviolet light, X-rays could travel much farther, heating and ionizing the more distant diffuse gas. Together, the stars and black holes formed a tag team of illumination. One slicing through the fog, the other warming the farthest reaches of the cosmic ocean. If you could have seen this era unfold from above, it would have looked like a universe coming alive cell by cell, glowing from within as light spread outward. Each bright bubble of ionization was a sign of cosmic civilization in its infancy. Tiny galaxies blazing with new stars carving out their territory in the darkness. Between them, the neutral hydrogen acted like a patchwork of night, slowly being eaten away by spreading dawn. Eventually, those ionized bubbles grew so large that they began to overlap. The fog of neutral hydrogen was no longer confined to pockets. It had been nearly erased. The universe, once opaque, was now transparent from one end to the other. Light from distant galaxies could finally travel across billions of light years, unimpeded. The cosmic dimmer switch had been turned all the way up, and the stars that once hid behind the fog now shone freely into space. Rayonization didn't just clear the skies, it reshaped the universe's destiny. The intense radiation changed how gas behaved, heating it enough to prevent small galaxies from forming easily. Some clouds of gas were stripped bare, losing their ability to collapse into stars. Others, enriched by earlier supernovae, adapted and thrived, forming more stable and efficient galaxies. The universe was becoming more structured, more layered, more alive with contrast and motion. It's no exaggeration to say that this period set the stage for everything that followed. The galaxies that emerged from the Rayonization era would go on to cluster together, merging into larger systems that eventually became the great spirals and ellipticals we see today. The light from this epoch, stretched and faded by billions of years of expansion, still reaches us now as faint infrared whispers. When telescopes like the James Webb Space Telescope peer deep into space, they are literally looking back to this age of awakening, to the universe's first true sunrise. Rayonization was more than a scientific transition. It was a cosmic transformation, a rebirth. Before it, the universe was a murky, invisible place, lit only by nearby sources. After it, light ruled supreme. The cosmos had gone from opaque to transparent, from hidden to revealed. The long shadow of the Dark Ages was finally gone. And though no eyes were there to witness it, this was one of the most profound moments in the history of existence, the moment the universe opened its eyes. From then on, starlight could travel unbroken, crossing unimaginable distances to illuminate whatever future awaited it, including, eventually, a tiny blue world orbiting a middle-aged star, whose inhabitants would one day look up and wonder how the dark first turned to light. After the first stars burst to life and their light tore through the cosmic fog, the universe began to organize itself on a grander scale. The small, scattered pockets of starlight that once blinked alone in the dark started to come together under gravity's persistent pull. For the first time, the cosmos began to resemble the tapestry of structure we recognize today, an intricate, glowing web of galaxies stretching across the vast expanse of space. The age of isolated stars was over. The age of galaxies had begun. Gravity, ever the universe's master architect, was once again at the drawing board. The first stars, born in small clusters, began to merge into larger groups. These clusters grew by collecting more gas, forming new generations of stars as they went. The larger they became, the stronger their gravitational pull, allowing them to sweep up even more material. It was a cosmic snowball effect. Small became medium. Medium became massive. And massive became majestic. But the process wasn't neat or elegant. Not yet. The first galaxies were chaotic, irregular blobs of stars, gas, and dark matter. They had none of the graceful spiral arms or smooth disks that would define their descendants billions of years later. If you could have seen them then, you'd think the universe was still figuring out its sense of style, an awkward teenage phase of galactic evolution. These early galaxies were compact and violent, filled with bursts of star formation and furious radiation. They collided, merged, and grew in spectacularly messy fashion. At their cores, dark matter continued to play its silent but crucial role. Invisible halos of dark matter surrounded these growing clusters, providing the gravitational scaffolding that held everything together. Without dark matter, galaxies would never have coalesced. The gas and stars would have drifted apart under the relentless expansion of space. Instead, dark matter's unseen gravity created stable wells where matter could settle, swirl, and shine. Each galaxy was a glowing island in a dark ocean, anchored by an invisible mass beneath its surface. As more stars formed within these young galaxies, the universe began to glow in earnest. Clouds of gas illuminated by clusters of stars painted space in brilliant colors. Deep blues from massive, hot stars. Warm reds from cooler, older ones. Nebulae shimmered where new stars were being born, while shock waves from dying stars sculpted the surrounding gas into complex, rippling patterns. Light and motion combined into a cosmic artwork billions of light-years wide. Over time, the galaxies started to take on distinct personalities. Some became vast, swirling spirals, their arms sweeping gracefully around bright, star-packed centers. Others evolved into smooth, elliptical giants, rounded and red, filled mostly with older stars that had long since burned through their fuel. Still others remained irregular. Peculiar galaxies twisted by collisions and gravitational encounters. The universe had entered its age of diversity, experimenting with form and function. Collisions were particularly influential in shaping the galactic landscape. Far from being rare catastrophes, galactic mergers were the main way galaxies grew. When two young galaxies collided, they didn't smash like solid objects. They danced. Stars passed through each other, pulled by gravity into new orbits, while clouds of gas collided and compressed, igniting intense bursts of star formation. These cosmic collisions could trigger thousands of new stars to form in a single galactic heartbeat. Each merger left behind a new, larger, and often more complex structure. A galactic makeover born from chaos. Inside these growing galaxies, more complex ecosystems were emerging. The interstellar medium, the gas and dust that filled the spaces between stars, became a dynamic environment. Supernova explosions enriched it with heavier elements, while gravity pulled that enriched material into new stars and planets. For the first time, chemistry and structure began working hand in hand. The galaxies were not just collections of stars. They were living, evolving systems, recycling their own material in endless loops of creation and destruction. In the heart of many galaxies, something extraordinary was stirring. Massive black holes, millions to billions of times the mass of our Sun, began forming from collapsing gas or the remnants of the first massive stars. These black holes acted as both anchors and engines for their host galaxies. As gas and dust spiraled into them, they released vast amounts of energy, often outshining entire galaxies. These became the first quasars, beacons so bright they could be seen across the visible universe. Galaxies, once defined purely by their stars, now had blazing cores that rivaled their own brightness. By this time, the cosmic web, the vast, interconnected structure of matter across the universe, was beginning to fully emerge. Galaxies clustered along filaments of dark matter, separated by immense voids of emptiness. Where filaments intersected, massive clusters of galaxies formed, gravitationally bound in sprawling cosmic cities. From afar, the universe looked like a three-dimensional spiderweb glowing with starlight. What began as a nearly uniform sea of gas had become a masterpiece of structure and symmetry. Each galaxy told a story written in light. Some were small and fragile, forming only a few 100 million stars before fading into obscurity. Others became sprawling giants, home to hundreds of billions of suns. Over billions of years, they would continue to merge, evolve, and refine their forms. The universe was no longer a static background. It was dynamic, colorful, and full of character. It's astonishing to think that from chaos and collision came order and beauty. The first galaxies were built through violence, yet what emerged were structures of breathtaking grace, spirals wound like cosmic whirlpools. Ellipticals shone like smoldering embers. The universe, once formless and silent, had finally found rhythm and shape. It had style. The galaxies that took form during this age were the ancestors of everything we see today. The Milky Way, Andromeda, the billions of other islands of stars scattered through the cosmos. Their creation marked a new chapter in the universe's story, one that would lead, eventually, to worlds orbiting those stars and life gazing back at the heavens. In the great gallery of cosmic art, this was when the first masterpieces appeared. The universe had gone from a featureless fog to a vast exhibition of structure and light. Galaxies had taken shape, and the cosmos, at last, had learned how to shine beautifully. For hundreds of millions of years, the universe had been an ocean of silence. It expanded, it cooled, it waited, but it did not shine. The only light that existed was the stretched, fading glow of the cosmic microwave background. Too weak for eyes, had there been any, to see. The cosmos was vast and beautiful, but utterly dark. Then, in a moment of breathtaking significance, the silence broke. The first stars ignited, and the universe experienced its second great awakening. The Dark Ages were over. When those first stars flared to life, it was as though the cosmos had opened its eyes after an eternity of blindness. The universe didn't just get brighter, it came alive. The light from those early stars began to race across space, illuminating the hydrogen fog that had dominated for so long. What was once cold and invisible became a landscape glowing with the faint blue light of massive young stars. These were not gentle suns like ours. They were cosmic giants, their ultraviolet brilliance fierce enough to transform the very nature of space. This era marked the universe's first true transition from potential to performance. For billions of years to come, light would never again vanish completely. The Dark Ages were a necessary stillness, a deep breath before the symphony. But this was the crescendo. Everywhere, in every direction, matter was collapsing into stars and galaxies. The universe was finally producing its own light, its own heat, its own chemistry. As the first starlight spread, it began to interact with the sea of neutral hydrogen that filled the cosmos. That hydrogen absorbed and re-emitted light, creating a glowing fog that shimmered across the young universe. For the first time, light and matter were locked in a cosmic dance, each shaping the other. The newborn radiation carved through the darkness, clearing out vast bubbles of ionized gas, pockets of visibility expanding outward like growing ripples in a pond. You could think of this time as the universe's first sunrise, though it was a sunrise unlike any other. The darkness didn't lift all at once. It faded gradually as more and more stars were born. Each new generation added to the illumination, amplifying the glow until the combined light of billions of stars filled the cosmos. There was no horizon, no single point where the light began, just countless sparks blooming into a cosmic morning. It's easy to forget how revolutionary this transition was. Before this era, there was no color, no light, no visible structure, just invisible atoms floating in the void. Afterward, there were colors, temperatures, and contrasts. The physics of the universe hadn't changed, but its personality had. The quiet expanse became a roaring stage of energy. Fusion burned in every corner. Radiation streaked through space, and the seeds of galaxies began to glow. The universe had moved from silence to spectacle. The end of the Dark Ages was not just the triumph of light, it was the birth of complexity. Once starlight filled the cosmos, new possibilities emerged. Photons energized gas, triggering chemical reactions that couldn't have happened in darkness. Ultraviolet radiation split molecules apart, while shock waves from supernovae compressed nearby clouds, igniting even more stars. It was a chain reaction of creation. Light begetting heat, heat driving motion, and motion giving birth to new light. And with light came time. For the first time, The universe had a rhythm that could be measured by brightness, by cycles of fusion and collapse. The cosmos developed texture and tempo, the slow pulse of creation beating across billions of light years. This era was not just a change in illumination. It was the beginning of the universe as a living, evolving system. In many ways, this moment was even more profound than the Big Bang itself. The Big Bang created space and time. This event created beauty and structure. The Big Bang gave the universe existence. The end of the Dark Ages gave it character. It was the moment when physics became art. Galaxies began to form recognizable shapes. Filaments of matter stretched into elegant webs, and light scattered in colors that would one day define nebulae and starscapes. The newfound brightness also carried its share of destruction. The radiation that illuminated space also stripped electrons from hydrogen atoms, heating the intergalactic medium and halting star formation in some regions. It was a double-edged sword, light that gave life, but also reshaped the conditions for future creation. Yet even this chaos was necessary. It set limits, imposed boundaries, and carved the architecture of what would follow. The universe was learning balance, how to create without consuming itself entirely. If you could have watched this transformation unfold, it would have been breathtaking. Imagine standing, somehow, in intergalactic space as the first points of light flared into being, scattered across a horizonless void. One by one, more appeared, like sparks catching in dry tinder, until the darkness glowed with faint starlight. The light would have been ghostly and blue, but unmistakably radiant, the universe's first glimmer of itself. As the last of the darkness faded, the universe settled into a new identity: luminous, structured, dynamic. The night sky as we know it, a canvas dotted with brilliance, was born from this shift. Every galaxy, every star cluster, every cosmic filament traces its lineage to this pivotal moment when the lights came on. From then onward, the cosmos would never again be truly dark. Even in the spaces between galaxies where the void stretches cold and empty, faint whispers of that first light still drift. The universe remembers. The end of the Dark Ages was not a single event, but a turning point, a threshold crossed after eons of anticipation. The light that emerged then was the light that built everything: the galaxies, the stars, the planets, and, eventually, the eyes that could look back and marvel at it. The darkness had not been a mistake, it had been preparation. And when it finally ended, the universe didn't just shine, it blazed. The cosmic night gave way to an endless dawn, and the void that had once been silent now hummed with the music of fusion and light. The masterpiece was underway, and the cosmos, illuminated at last, began to show just how beautiful existence could be. The story of the universe is, in a very real sense, our own autobiography written on a cosmic scale. Every breath you take, every heartbeat, every thought flickering in your brain is powered by matter that once floated in the deep silence before the first stars were born. Long before Earth, long before galaxies had names or shapes, the raw ingredients of your body drifted through the void, anonymous and patient. You are built from the ashes of starlight, but your story begins in darkness. When the first stars flared to life, they were more than distant beacons. They were foundries. Inside their blazing cores, simple hydrogen and helium were fused into heavier elements, the building blocks of complexity: carbon, oxygen, nitrogen, and iron. The substances that would one day make DNA, water, and blood were born in those violent furnaces. And when those first stars died, they didn't take their creations with them. They scattered their enriched remains across space, mixing their stardust with the cold hydrogen that still lingered from the beginning. Over time, that enriched matter collected again, pulled together by gravity into new generations of stars. Around some of those stars, swirling disks of gas and dust formed, the first planetary systems. Tiny grains of rock collided and stuck, forming pebbles, then boulders, then worlds. On one of those worlds, circling an ordinary yellow star in a quiet corner of a spiral galaxy, chemistry found a way to think. It's an extraordinary idea. The atoms forged in the death throes of long-lost suns eventually became aware of themselves. The universe began as something utterly mindless, just energy and expansion. And yet, here we are, tiny creatures on a pale blue planet, capable of looking back and reconstructing that journey from nothingness to consciousness. We are, in every sense, the universe waking up to its own existence. But before that awakening, there was so much waiting. Billions of years passed between the first light and the formation of Earth. Generations of stars lived and died, enriching their surroundings, deepening the chemical palette of creation. By the time our solar system formed, about 9 billion years after the Big Bang, the galaxy had already become a well-stocked workshop. The hydrogen and helium from the early universe were still abundant, but now there was carbon for life, silicon for rocks, and iron for planets with molten cores. The material that would become our world wasn't special. It was ordinary cosmic debris. Yet, through gravity's tireless work, that dust gathered into the sun and its surrounding family of planets. The third of these planets, small and temperate, found itself in just the right orbit for liquid water to exist. Here, the leftover atoms from the first stars began forming molecules, simple at first, then astonishingly intricate. Chemistry became biology, and biology, in time, became awareness. If the early universe was a blank canvas, the emergence of life was the brush stroke that gave it meaning. It took the cosmos billions of years to assemble the tools required to ask questions, to marvel, to dream. The atoms that once drifted silently through space now compose poets, scientists, and children staring at the stars that created them. The darkness that once seemed endless now exists only as a memory in our story, a reminder of where everything began. The connection between us and that ancient void is not metaphorical, it's literal. Every carbon atom in your body was fused in the core of a massive star. The calcium in your bones was born in an explosion so powerful it briefly outshone entire galaxies. The oxygen in your lungs came from generations of stellar deaths that enriched the universe long before Earth existed. We carry the memory of those events in our chemistry, our existence an echo of fusion and gravity, written into every cell. Even the water that fills our oceans and veins tells the same story. The hydrogen in water is primordial. It's been around since the universe was minutes old. The oxygen, however, is the product of stellar alchemy. When you drink a glass of water, you are literally blending the universe's earliest atoms with the remnants of long-dead stars. In a very real way, the cosmos recycles itself into life. As the universe continued to evolve, galaxies merged, stars were born and died, and planets multiplied. Amid that cosmic bustle, on the Earth, life flourished. For eons, it remained simple, bacteria and algae quietly remaking the planet's chemistry. Then complexity emerged. Plants, animals, and eventually minds capable of wonder. And with that wonder came an inevitable question. How did it all begin? The same atoms that once drifted silently in darkness had built brains capable of curiosity. It's almost poetic that we, who come from starlight, spend our nights looking back at the stars. We are tracing our own ancestry, decoding the clues left behind in the light that reaches us across billions of years. When astronomers peer deep into space, they are not just looking outward, they are looking backward, watching the very processes that gave rise to them. In studying the cosmos, the universe is, in essence, studying itself. The journey from darkness to us is not just a story of science, it's a story of transformation. The universe began as chaos, settled into silence, and then found balance, light, and beauty. Every stage, every explosion, collapse, and fusion was necessary for our existence. The hydrogen that once floated quietly in the dark would, through gravity's patience and physics' creativity, one day become the spark of a human thought. So the next time you look at the night sky, remember this: you are not separate from it. You are the continuation of that first light, the descendant of the universe's earliest dreams. The darkness that once filled everything wasn't an ending, it was a beginning. From it came stars, from stars came life, and from life came consciousness capable of asking why. The cosmic night gave birth to the dawn, and that dawn gave birth to us. The universe, in learning to shine, also learned to wonder. And through us, it still does.